Alrighty then, let's start with a new problem. This is to sum. Okay. So we can solve it with the hash map. Okay. So, given an array of integer nums and an integer target, return indices of the number such that the two add up to target. Okay, you may assume okay, so I have this done already in C. We will go with Python 3, thank you. Right. So we want to return the indices that add up to sum, right? Okay, so we have a target, right? And then we have a sum. So how can I store? You may assume that each input have exactly one solution and you may not use the same element twice. You return the answer in any order. Okay, so you have 2 and 4, right? 3 and 3, 6. Okay. Only one valid answer exists, right? Maximize full screen. What is this? Maximize. Okay, full screen. Okay. Okay, so how can I use it using hash maps? I want the target, right? So I have this array and target, right? Hash maps. How can hash maps too much? Think about right. Okay, how can hash maps be of use here? Okay, so given an array of nouns, integer, target, and indices of two numbers such that they add up to. Alright, so I have a target, right? O of n solution. Target um 2 and 7, 11, 15, target equals 9. Okay, we got this. Okay. Okay, what if I import default dict, right? And hash maps be use of here. Like I can start with this and then I keep subtracting, but it won't work, right? can I? Okay, so with if I convert it to sets, this would be invalid, right? Okay. Hash maps, right? We have 0, 1, 2. How can I do this with hash maps? Let's create a count, not count really. That's a dictionary. I dictionary. Default dicт of ents. Then for x and nums, I can do default. No, but I don't really. Okay. Right. So we have a target, right? Linear search, obtaining a target. So we can also do that with a array. How can a hash map be beneficial here? Right. How can a hash map be beneficial here? Right. Okay, so I have this array, right? 2, 7, 15, 2, 7, 11 and 15. And I have a target of 9, right? Okay. Then how can I say if I map let's say indices? Okay, if I map index and value to a hash map, so it would be something like 0, 2, 1, 7, 2, 11, 3, 15. Okay. So okay, let's see. We want to add because I want two indices such that what did I do in C? Two loops, right? To sum.
Okay guys, let's solve the very first question on LeetCode, which is toSum. So we're given an array of integers, nums, and another add up to 9, assume, and there's an example. Well, technically 3 plus itself is equal to the target of 6. The last example shows we just can't use the same 2, 3, and our target value is 6. We know we are going to want to return 0 and 3 because those are our indices that add up to 6. So the easiest solution is to look at all possible pairs of numbers. So at 2, and we will then go through, we have 3 answer. Now you'd have to look at this number and compare it to this, this, and this. And then you would have to take this number and compare it to all of the other ones. That is going to give you an O of n squared runtime, which is the keys, and will Now, can we use a hash map? We have nothing at first, so we'll definitely make the numbers the keys, and we'll store its associated index. And so we'll go through, we'd get that 2 is stored at index 1. Now, when we're at this point, we actually get to the fact that we've seen 2 before, and so when we go to put that in the dictionary, actually it's just going to update the value. And getting the earlier index, we'll just use the later one. We'll do 2 is 2, and same thing with the 3 over here. We are just going to update its index, and we can x is 3. We're looking for a value y, which is equal to 6 minus 3, which is equal to 3. We ask if that is a key in our hash map in constant time, and so it is. It is right here. Okay, so what's the index for this?
Okay,
Well, note.
that's right. See, I literally thought about that if we should subtract it, and that is it. Okay, so we create a hash map of values comma indices. So I'll go for I int range. For I in range len of nums. I'll create idict equals empty dictionary. So I'll go idict of I equals idict of nums of I equals I. Let me go print idict. To 0 11. Nice. Okay. Okay. Literally, bro. That is what I thought, that we subtract this, but I didn't had the idea to check that if subtracted this exists in the dictionary. Okay, so that is basically what we check, if it exists in the dictionary, and we go sequentially and keep subtracting the keys from the target and check if the result that subtraction exists in the map. If yes, then we create a list. If yes, then we create a list with both the indices. If not, then we simply look ahead. Okay, so I'll go result is an empty list, and we'll go for x and nums. Then we'll go second equals target minus 0, 1. Okay, and if it is the same, how would we know the index, right? If it is the same number, how would we know the, okay, we can, this should be plus equals to index, so this should be a default tick of int, and I'll say plus equals to indexes, right? Target minus nums of I, target minus, okay, target minus x, right? So I'll just call it y. If y in idict and y is not equals to x, if y in idict and y is not equals to x, then we can return simply, let's see, idict of y, we're going to return a list, idict of I, idict of x. So let's try run this. I think, yeah, because 2 and 7 and 2 and 4, that, okay. And if y in idict and y equals x, okay, else if y in idict, okay, if y is in idict ticked, else y equals x, okay, if y in idict and y equals x, what we can do is we can return the dictionary by subtracting, right? Both are equal, right? So want new index equals it should be I. Okay, I should be iterating with, okay, if it is I, right, I plus index. Okay, then we use sequential keep subtracting the keys from the target and check if the result of the subtraction exists in the map. If yes, then we create, okay, if y is an idict and y equals x. If both are equal, if y in idict and y equals x, then I want to calculate the new index, right? Both the values are equal in nums, right? Maybe 3 y equals target minus x. Okay, hold on.
Notice that this is quite fine actually, because we have our earlier index and the one that is stored in the hash map is the later index. So we can ensure that 0 is not equal to 3. We can ensure that our indices are not the same one, meaning that this is a valid solution. Now we know for this solution, we just need to return the indices, which are going to be a list of 0, 3, 3, 0 would work as well. And we can actually guarantee that a solution exists as we go through the array because of the constraint of the problem. As we can see, you may assume each binary or hash in the range set 80, and we want that to equal its index. And here one. And we'll do another pass through the numbers. We'll do for I.
Okay.
I in the range, which is equal to I. If y is in the hash map, that's great. We have a sum, except we also need to ensure that the index, which is stored at h at y, we need to make sure that's not equal to the same index we're using right now. Turn the list of our two indices, which is I and h at y. And we should be able to run this. We'll see that our solution is equal to the same index.
Okay. So, because it stores the later index. Okay. Right. Okay. Okay, so I don't need to go plus equals. I can simply, so we don't, let's start with a new simple index ticked nums of I equals I, right? Nums of I, the I in range and nums, then we again range then nums, we go y equals target minus nums of I. Then I want to check if y in I ticked and y is not equals to nums of I, right? We check if it is not equals to h. Okay, I want to check that. Want to check if I ticked of y should not be, that these both indexes should not be equal. Okay, then we return a list of y, sorry, I rect of y comma I, right? Okay, now we will move on to 2 pointers. Let's learn about this 2 pointers, the squeeze.
Hey guys, Greg here. Today I'd like to talk about an algorithm known as Hey guys, Greg here. Today I'd like to talk about an algorithm known as 2 pointers. And it's kind of silly because we say pointers, but really we mean indices. So generally what you're doing is given some array, and by 2 pointers, generally we mean that you have one at the beginning, which I'll call L on the left side, and the other R on the right side. And generally they work towards each other into the middle. Now more generally, 2 pointers is kind of anything where you have 2 indices, and so you could also argue an algorithm called sliding sliding window is also 2 pointers, 2 of them at the beginning, and they kind of slide across to the end of the array. However, in general, when we refer to 2 pointers, I actually kind of want to replace this with just called the term squeeze. When most people say 2 pointers, they refer to one index at the beginning, another at the end, and they kind of squeeze towards the middle. Okay, so to learn about 2 pointers, we're going to solve the problem called squares of a sorted array, and I'll jump this over to my LeetCode video where I show how to solve that problem. So we're given an integer array of nums, and it's been sorted in non-decreasing order. I hate when they say that. It basically just means that it's increasing, but there might be duplicates. So we need to return an array of the squares of each number, also sorted in non-decreasing order. Again, also sorted in ascending order. So if we were given the array of nums as -4, -1, 0, 3, 10, so it is sorted in increasing order, what we want to do is square all those values. So we'd have 16, 1, 0, 9, and 100, and we want those in the order. So notice they're all going to be positive numbers because positive and positive makes positive, and negative times negative makes positive. So you want the sorted order of the squares of all of the original numbers. And the reason that's kind of tricky is because originally it's in sorted order, but if you were just to square them, well, it's not sorted anymore. But there's some properties of it where we're going to figure out how to do this well. Okay, so let's use the same example here. Let's just quickly square the numbers. So we'd get 16, 1, 0, 9, and 100. And let's remove our original list because we really don't need it anymore. So what we have here is our squared numbers. The easiest way to solve this problem, kind of the brute force solution, is just to say, okay, well, we have the numbers. Why don't we just sort it? We could do that in big O of n log n time. You know, it's not the worst runtime, and it would immediately sort it. You could do this in place if you want, or just return a new array, and you are going to get the solution that you'd want. And you could return that, and it'll work in big O of n log n time. Now let's step back to where we got our squares and try to beat n log n. So if you're trying to beat in n log n time, the runtime you're probably hoping is to get rid of the log n part, and you're probably just trying to get O of n. So let's try to get an O of n runtime. Now they're not already in sorted order, but they actually have this kind of clever property to them, where your biggest values are going to be on the outside. So we'll say that we're building up a new array, and the first value will be the biggest value, which is 100. Now we're actually just going to slide this over here, which is why we call this a 2-pointer approach. So we're basically using 2 pointers that are tracking these different indices here. They're really indices. And now from this point, your biggest value is either this or it is this. And by the way, I'm going to call this index as L for left and this index as R for right. Or index or pointer, we really mean the same thing here. So we have our 2 pointers L and R. Our biggest value must be either the array at L or it is the array at R. It happens to be the array at L, and so we are going to kind of plug in that we have that value there. That is our second biggest value, and we move L towards the middle here. We have again that our biggest value must be one of these two, either the array at L or the array at R. It happens to be at R. We are going to plug in our value here, and so we'll move R over to the middle. Our biggest value must be one of these two. It happens to be L. We're going to move L towards the middle, and then we would say, hey, we have that they're equal to each other. So we are going to get our new biggest value, which is equivalently our smallest value at this point, because we are actually at the end of the array. At least we've used all the numbers. And here, it doesn't really matter. If your values are equal to each other, we actually have that the array at L is equal to the array at R. And that could have happened at any stage. That actually could have happened if this was a 16 here. If they were, and say R was over here and L was here, it doesn't actually matter which index we used. So if R and L pointing to the same value, let's say, for example, that we just moved L over, it doesn't really matter which index we used. Either way, we're going to run into this scenario where R is now not really named appropriately because R for right is actually on the left. So as in they've kind of done this crisscross thing that we no longer have that L is less than R. And more specifically, we no longer have that L is less than or equal to R. We have that L is strictly greater than R here, meaning they've kind of done this crisscross thing. They've passed each other. And so this is kind of where we're going to run our while loop condition. We're going to run this while L is less than or equal to R. We're going to build up this array here. Now I'm sure you've seen the only problem that we have is that these are actually sorted in the wrong order. But to just flip around this array, you can flip around this array in O of n time. You can actually do it with a 2-pointer technique I encourage you to try. Okay, so let's write our code. We'll get left located at index index, which is going to be located at the length of nums built in place to the value is actually bigger than the absolute value that is at the right at the results list. Move it closer to the center. Otherwise, we're in the opposite case, or they're equal to each other, and so it doesn't really matter what you use if they're equal to each other. So we result dot append the nums at the right square by 1 to a. It's just that we have result in the complete wrong order, and so you can space it's reversed. If we were left or right, all of the number thing to do of n time. If you wanted to write it yourself, the space complex, that's the only thing that we're give us. We're storing the result that we must actually give back. Like what we possibly as any extra space, then sure, it's O of. It's actually a part of the return. Well, I'm not really using any extra space. I'm just using space that you required us to use. Okay, but there's our code. I hope it was helpful, guys. Drop a like if it was, and have a great day. Bye-bye.
Okay. Okay, so I have this problem maturity element. Let's check this. If given an array nums of size n, return the maturity element. The maturity element is the element that appears more than, that is n factorial over 2 times, n over 2 times. Okay, you may assume that the maturity element always exists in the array. So this is the easiest thing, right? Hold up, let me do some. I want to show the answer. Right. Alright, so we have to some maturity element. This is, I'll just go from collections, import default dict. Then I can just create a counter, right? Count default dict of ints. Then we go for n in nums, count of n plus equals 1, and I can simply return what can I return? Output 3. Then I can find the max of, right, two. Follow up, could you solve the problem in linear time and of one space? Okay, n by 2 times majority element replace n by 2 times. Okay, so first create a count. Okay, so what I want to, let me save this over here. Okay, so now I want to find the key with the max value. So I want max of max of all keys so I can simply go for kn count I can make a max equals 0 right now. Then okay, max equals count of, well, I don't know the count, so for I and range len of nums minus 1, then I can count max equals 0. I simply go max equals max of, or I would say maturity equals max of count of I comma count of I plus 1, right? And simply then I can sorry, no, this would not okay, I want the maturity element, right? So this is count I want the index, right? No, right, I want the element. So I'm storing the key here, right? Okay, so I want to get, right, I want to get the key with the maximum value. That is what I want. So I count default create account, I have account, and find the key with the max value. Okay, how am I going to do that? I think I have to go search in the count, right? I can okay, major equals 0. Okay, then I go major. Okay, I can start with a maximum. No. Okay, then I'll go if count of k is greater than major, right? Then major count of k. Okay, I'll just go nums of 0. Count of major, then I go major equals k, and then we at the end we return major, right? Is enough. We create a map and then we measure, we specify, we go count and then return measure, right? Okay, this is a slow solution.
Hey guys, Greg here. Let's solve majority element, LeetCode number 169. Majority element 2 times. And this little symbol here is the floor, so round it down. So you may assume that the majority element is 3, and if you have 2 element would be 2. Okay, let's use this example. We have 2 appearing in over half of the array positions, therefore it is the majority element and what we'd return. Now the first solution that comes to mind is building up a hash map, where basically it's the number of you could go through the ones you have frequency. So you could basically create this hash map in O of n time, and then you could get the maximum frequency in O of n time, and then you just return that corresponding number. So that is going to take a time complexity of big O of n, and the space complexity of this is also going to be familiar with Python empty num at the num we'd say before. So we'll say that variables basically to and number that's going to be associated with the max count. Okay, then we can loop through the dictionary. So for each key,
No, what is max count?
max count is going to go and find the highest frequency, and
Okay.
answer will be the number that's going to be associated with the max count. Okay,
Okay.
then we can loop through the dictionary. So for each key and value in the counter.items, that loops through the key value pairs, if the value is greater than the max count that we've seen so far, then you'd want max count to be that value, and you have an updated answer so far. So we'll set answer equal to the key. So after this thing runs, we're going to have max count as the count. So that after of this would be big O of n. The space complexity is also going to be big O of n. So if we were to submit that, that is going to work, but we can get a better solution than this. Okay, so the idea is to so far have a candidate, which I'll just call answer. Also going to have a variable called count, which is going to be initialized to 0. Now we'll loop through the array from the beginning, so we'll start at the 3 first, and we basically ask these two questions in order. Firstly, is our count equal to 0? Yes, it is, and because the count is 0, that means we're going to update our answer to the number we're currently looking at. So answer is going to be set to 3. The second question is our current number matching what our answer is? Yes, actually it is, and therefore we're going to increase the count. So we basically say we have one count. It's kind of like a tally for this potential answer that we have. Okay, and we keep following that rule here. So we go through and we see a 2. Okay, well our count is not 0, so we're not going to update our answer. However, this current number of 2 does not match our answer, and so when that happens, we actually decrement the count. So this count is going to go down to 0. That's going to cause this to happen. When we look at the next number, we ask the question, is our count equal to 0? Yes, it is. And so when that happens, you update our answer. Okay, we really matches, kind of trying to suggest, and we see, and so our count, so we don't update our answer, but they are mismatching, and so our count is going to go back down to 0. This means that next time when we go over here, our answer is actually going to be set to our current number, and so it's going to be set to 2. You can see we basically just lost our ability to think it was 1 because we saw 3 2s in a row here. And so we will get a count is equal to not match. We are going to set our count equal to
then whatever the answer is
reset to this last number, which happens to be 2, and that's going to end with a count of 1. And ultimately, you would return our answer. So why the heck does this algorithm work? It's really weird, isn't it? I handpicked this example because I think it's very interesting to see that basically all the stuff that we did up to this point, it really didn't matter. It ended up just getting set to this last number here. Now, while that's not always the case, it shows the intuition. If you have 1, 2, 3, 4, 5, 6, 7, 8 elements here, well, if you didn't find the majority element here, then that means that it must be over here. And since there's only one element here, it's actually going to be set to that number. So if there was actually a 3 here, well, then it would have to be 3. But that doesn't work because that's an invalid example. Because you know that the majority element exists here, there is a number in the array that occurs in over half of the array's positions. If you've looked at all of this stuff here and you didn't find it, then it's got to be over here. Same thing if it was a different example, like it was a bunch of 2s over here, so we'll say 2s over here. Well, if you did find it over here, which you would, if you look in over half the array's positions here, well, then the count's actually going to be so high here that you actually can't get it away from being 2. Even if all of these were 1s, for example, it's already been found at this point, and so your answer would still be 2. Okay, so the idea is to set our answer equal to any initialization. Exactly what we said. For each number in the numbers array, first thing you do is if the count is ever equal to 0, we're going to update our
answer.
If the answer is equal to our number, then the count is going to go up by 1. So if they are matching, then we have basically more proof that that is our actual answer. And otherwise, if that's not true, then count is actually going to be decremented. So it will go down by 1. If
Who is calling? Okay, so
We didn't
with
match.
this,
We basically lost proof that that was the majority element. Okay,
this
and after this is true here, you will actually have set answer to be the correct big O of n. To submit this is going to work, and I hope
space
this
of
was
1.
helpful, guys. Drop a like if it was, and have a great day. Bye-bye.
Okay, so I solved it right my way. This is my solution. Two pointer, 3. This is maturity element. Oh no, sorry, but it is still here. This is 7 maturity element, and okay. So this is my solution. A better way would be a linear search, right? Okay. So this is my solution for LeetCode. What is this? LeetCode 169 maturity elements. 169 maturity element. Okay. So solved. We also have a linear approach. Okay, right. We also have a linear approach, which is goes like this. We define answer and a count equals 0. Then for n in nums, we go if okay, so we check if count is 0, then we set answer equal n, right? Then if r if count is 0, we set answer equals num. Then if answer is not equals to the element, then we not equals to the element, then we decrement, right? Count must go down. Okay, we check if answer equals n, count is 0, count is 0, set and then we increment count plus by 1. And if it is not equal, then we decrement count by 1, right? And at the end we should have a answer. Okay, written outside, it is outside of function. Isn't it supposed to be like this? Oh, okay. Okay, it will give me an indentation error. Okay. Right. So we have time complexity of O of n and the space complexity of O of 1. Okay, so So we are linearly goes through the array and maintain an maintain an active count. Active count of the elements. If the element appears more than half times, then it will be the answer in the end, since none of the elements would since none of the elements would be okay, since none of the elements would no, and basically, and this is the solution, linear solution. Okay, am I right? Algo map 60 to some algorithm. So linear solution from algomap.io. Okay, that is how you can current max. Okay, so let's call it a day today.